This is Calculus AB for Friday, September 25th. It's not November yet. Today we took a look at some of the homework from last night, some of the ones on this worksheet. Number 19 and 20, talking about differentiability. Any function is not differentiable where it has a cusp or a corner. The directions say use left and right hand derivatives, so we're going to observe that the derivative coming from the left, my slopes of my tangent lines are negative and getting more negative. Coming from the right, they're positive and getting more positive. The left and right hand derivatives don't match, so the function is not differentiable at this point. And there's a similar argument for number 20. Looking at number 23, we did find a value of k for which the function is continuous. And if I look at limits, it turns out that the left and right hand limits of the difference quotient also match. So the function is differentiable when k equals -2. And we took a quick look at number 28, our original function, and looking what the tangent lines are doing. We noticed that at the top of a hill and at the bottom of a valley, we have a horizontal tangent line, which means the derivative is 0. So the derivative is in pink here. Where we have a horizontal tangent line at that x value, the derivative is 0. At this x value, the derivative is 0. Then we looked at slopes of tangent lines again. Positive, so I know my derivative will be above the x-axis. Negative over this side, so I know it'll be below. And if I connect the dots and make observations about how fast those slopes are changing, I get something that looks like the pink graph, which is in fact cosine x, which is in fact the derivative of the sine function. Then we've been doing difference quotients, f of x plus h minus f of x divided by h. The limit as h approaches 0. We've been doing those for a long time. We're going to do them a little bit more, but the goal is to find some faster ways of finding derivatives. The derivative of a constant, I picked 4, but any constant, the same thing will happen, is 0. So this is anything with a star is one for the memory sheet. Derivative of a constant is 0. Then we looked at functions that look like x raised to a power. I suppose we could call those power functions. And some different people did some different ones. And this is what we found. 1 over x I could write as x to the -1 power, and its derivative using the difference quotient is -1 over x squared, which I could write like -x to the -2. And that's what we did for all these functions. And we noticed, looking at the pairs, a function with its derivative, in general, if I take the derivative of x raised to a power, I get the old power times x to 1 lower power. Taking x to the third as an example, the derivative of x to the third is the old power 3 times x to 1 lower power. 3 minus 1 is 2. And we can use that henceforth and forevermore to take derivatives of functions that have powers in them, such as x to the 42nd. That's definitely a big one for the memory sheet, is 42 times x to the 41st. This one would not have been any fun with trying to use a difference quotient, the cube root, also known as x to the 1/3. But with the power rule, it's not too bad. Old power is 1/3 times x to 1 lower power. 1/3 minus 1 is -2/3. I could also write like this if I wanted. Couple other derivative rules. The constant multiple rule and the sum and difference rule. So the constant multiple rule says if I have a function multiplied by a constant, a number, I can take the derivative of the function and multiply that by the constant. The sum and difference rule says I can take derivatives individually and add them back together. I'll put a minus under there. the ones that we have so far allow us to take derivatives of any polynomial function. Here's how that's going to go. The constant is going to keep multiplying away. The derivative of x to the third is 3 times x squared. And I'm going to do that for each of the other pieces. Derivative of a constant is 0, and then we simplify. We already noticed that it surely looks from the graph like the derivative of the sine function is the cosine function, and it is. So we looked formally at the derivative of the cosine function using back to our old friend, the difference quotient here. Cosine of x plus h, we have an identity for that. Cosine x, cosine h minus sine x, sine h. Then we looked for some things that look familiar. I see a sine h over h in here. My other two terms each have a cosine that I can factor out. So I rewrote all of this, just rearranged a little bit. It's all the same stuff. I have negative sine x sine h over h, just the middle part there. And we know that sine h over h goes to 1 as h approaches 0. So this says negative sine x times 1. The rest of this, the other two sides here, I can, my whiteboard just fell off my wall, factor out the cosine. And again, we have a familiar limit here. As h approaches 0, cosine h of minus 1 over h goes to 0. Hopefully that's on your memory sheet too. So this whole term is gone. All I have left is negative sine x. So the derivative of the cosine function is negative sine x. The derivative of sine x is cosine x.